and I'd like to present Aric Vyhmeister from the Standley Lake Stargazing, and he is here to present on telescopes. So Aric, if you'd like to just tell us a little bit about yourself and your organization.
Okay, well, thank you, Cheryl. It's always good to be here. Um, I help run, along with two other guys, we run a group called Standley Lake Stargazing, and we are just a community science outreach and astronomy group. So typically, in a non-COVID year, we would just go around to the different libraries, parks, whoever wants to have us, and we'll just set up telescopes and show people how cool the night sky is and how our small little corner of the universe is really awesome. And we often do, myself, Freddie, and Ron Haverman are all engineers of various types, and so we often talk about spaceflight and just space enthusiast topics in general, in addition to very hands-on applied observing things. So we offer free programs every Wednesday night. I know I've seen actually a couple of you there. It's always great to have familiar faces in the audience. Those are free and open to the public at any time. So if you're interested in this type of thing, there's always new material at 6 o'clock every Wednesday. I'll share the link at the end if you're interested in that, or you can always contact Cheryl or get a hold of me. I believe the link is in the meetup announcement. So today we're going to be talking about telescopes. Now, I'll just put this disclaimer out at the beginning. There's way too much about telescopes to cover in one presentation, so I'm not even going to try to do that. What I'm going to do is kind of whet your appetite for what they can do, give you a little bit of the history, and then what they can do at the professional end of things, as well as a little mix of interesting information if you're in the market for one, or if you already have one and you're curious what it does. That being said, I like these to be very interactive. The main differentiating feature between something like this and something you could just look up on YouTube or read in countless articles that are excellently written online is that we can stop and ask questions based on what you're seeing. So I know some of you probably do have telescopes that you're familiar with. Some of you probably have no clue and maybe not an interest in it. That's totally fine. But if there's anything that piques your curiosity, feel free to just interrupt at any point and ask. This is very casual, not formal at all. I know I tend to go fast. There's a lot of things I want to cover because it's really interesting, but don't feel like that's not an invitation to interrupt. And I'll try to monitor the chat. And if you could help me out, Cheryl, if someone does put a comment in there and I keep going, which I have a penchant for doing, just let me know and I'll stop and catch a breath and see what we're looking at. Okay, so today's program, I've done this several times in the past, and I've kind of incorporated some of the feedback, the different questions that come up. I'm deliberately changing the focus a little bit from giving a lot of hands-on details, so we won't go through as many formulas, calculations. I'm going to assume that if you're interested in this, this will be just a pre-primer to going out and looking at one or looking on the internet to buy a telescope. I normally would cover a lot more detail about the different types of telescopes and what you should be looking for as a buyer. This time I'm just going to give you more of a conceptual sense of that, and then we'll leave the calculations for later. But if you are interested in learning more about that, we'll be doing this with the astronomy group, Standley Lake Stargazing, in I think it's 2 weeks' time. It'll be the more in-depth applied version. So if this is something you're interested in and you want to actually get more detail because you're in the market for it, feel free to join us for that. Details will be on the website, and I can connect you with that if you're interested. So let's do something different first, just to get started. I'm going to actually share my planetarium software here and show you something that I think is really fascinating. I mentioned we talk about stargazing and spaceflight topics, and this is kind of the nice little intersection of both. So we're going to look at Mars real quick. If you haven't been following the news, NASA launched its very cool mission, Mars 2020. It launched last year in the summer, and it just arrived Mars on Thursday and sent down the Perseverance rover. So I think it's really interesting to look at Mars now because it's in the evening sky. It's very easy to find, knowing that that just happened. So here's how you find it. Right now we're really lucky because the moon is pretty close to it, so I'm just going to use that and skip all the other constellation things and directions. This is just look for the moon, look to the right of it. You'll see this little cluster here. This is called the Pleiades, the Seven Sisters. It looks like, if you have good eyesight, it looks kind of like a miniature version of the Big Dipper. It's very distinctive and very bright, so you'll probably see it as a cluster of stars. So just make a mental note that that's there. And then the brightest orange looking star right next to it is actually Mars. So straight line from the moon back there. Pleiades is right next to it. That's what it'll look like tonight at around 6 o'clock. But when you look up at that, know that you're about 12 minutes behind seeing the actual light that left the planet, because it's far away from us and light isn't instantaneous. And there is a brand new rover and helicopter on the surface of Mars. So, yeah, find the moon, just go to the right, and you'll see it. And it'll be that way for the next couple of nights. Now, the moon will move substantially from night to night, but the Pleiades is a good solid reference. So if you can find that, just make a mental note, and you'll be able to find that for the next couple weeks. All right, let's go. Let me just share my correct screen with you. Okay. All right, and could someone just confirm that that's showing up? Should say all about telescopes.
Yes.
Okay, good. I used to have that nice little green frame around it to make sure I was broadcasting, but here we go. Okay, so let's just talk real quickly about the Mars 2020 mission. We'll get to telescopes in 1 second, but this is just very relevant and timely. I actually got the privilege of working on this for about a day. The heat shield was handled here in Denver, and so I used to work as an engineer with Lockheed Martin Space Systems down in Littleton, and our group did some of the inspections on the heat shield before it was sent out. So what happens is when it gets to Mars, roughly well over 90%, I think it's close to 99% of the energy of re-entry is displaced by the heat shield. It forms a shock wave as it comes in at orbital speed, and then that heat shield pushes the air out of the way really fast. It's not really air, though. It's a different atmosphere. It's only 1% as dense as the Earth's atmosphere on Mars. So it can't slow it down as much as it needs to just with a heat shield. So at the very last little bit, a parachute deploys, and that slows it down to this interesting bit here where the parachute then pops off with the back shell, and then this thing called the sky crane powers the descent the rest of the way down. The reason for that is there's just not enough drag. You can't pack easily a big enough and light enough parachute to get you down to a soft touchdown on the surface without adding more weight, and then you have all sorts of other drag problems. So to solve that, engineers use the parachute to slow it down substantially and then let the powered sky crane set the rover down with a powered controlled landing, and then it severs the tether that's holding the rover. This is Perseverance down here. And then it uses its remaining fuel to fly off, and it's never used again, but they just want to get it as far away from the landing area to make sure it doesn't damage the components here. Everything worked great. You can watch an image of the landing. You can see a picture taken from the sky crane looking down at the rover. NASA's publishing that. They're downloading some of the footage and imagery from that. So in the next couple days, we should be seeing some very high-res images. There's actually an old video out there now of Curiosity landing with a very similar method that was only at, I think it was 6 frames a second, but using artificial intelligence, someone was able to interpolate the frames and then speed it up to, I think, 60 frames a second now. And you can actually find this. If you're interested in that, let me know, and I'm happy to find it again and send you the link. Really interesting to see it in smooth motion, but hopefully this time we'll get to see that natively from the rover and see what the landing looked like in a way that we couldn't in real time. So the heat shield, this is just the part I got to work on. This is actually taken right next to where my old office used to be. I was up in this little balcony area behind that panel, just these little nasty old cubicles, but out in the floor in the factory, this is in Littleton, they took the heat shield out of storage. It was actually a clone from an earlier mission. They built 2 at the same time using the same research. I believe it's for the Curiosity mission originally, but Perseverance is almost the same size and weight in terms of dimensions, at least, as the Curiosity rover, even though it has substantially more instrumentation on board. But to save costs and R&D, they just said, let's just build the same thing twice rather than build a new one because the mission's close enough. So they pulled it out of storage a couple years later, and they wanted to make sure that it was working okay. So my group just had a very small part in making sure that the the drawings matched the part as it was measured on the floor after coming out of storage. So this is just a really cool thing to see in person. The heat shields do look a little different than the ones you've seen on reentry vehicles used for Earth entry, just because they have a different atmosphere to contend with. And then the weight distribution is different, and there's all sorts of really interesting things that the aerodynamicists have to deal with. So the shape does look a little blunter than we're used to seeing, but it works very well, and we know now that it functioned successfully. So it's just a cool moment for me to think, too, that I got to touch a little piece of a thing that's now, well, not on Mars. It's burned up in the atmosphere, but, it's out there. So it brings space a little bit home. So then going out and looking at it tonight is another cool way to connect it. So knowing that this rover's out there, go and see Mars tonight. You'll feel a little more connected with the universe around you in a small way, I hope. Okay, so now telescopes. When you look at this image, most of us have never seen anything close to this. Now, one question a lot of people have, myself included, is why can we take a picture of this, but why and not actually see that when you go outside? Well, you can get a little closer if you get fully dark adapted, and I know I've kind of talked about that a lot in previous presentations, but you have to wait 25 minutes without any sort of white light entering your eyes to get fully adapted. Once you see that, you can actually make out an order of magnitude fainter objects than you can, or more, using daytime vision. So you have to be patient and wait, and you can see quite a bit more, but you still can't see this. There's color, there's all sorts of details and shapes that just your eye will never see. Well, what's happening here is there are more photons present, and photons concentrated on our eyes is what we perceive as brightness. There are two ways to get things to be brighter. One is to let the photons accumulate over a long period of time. So that's long exposure, like in astrophotography, or if you've done any sort of nighttime photography. It doesn't necessarily gather a lot. It's a slow trickle, but it adds up over time if you keep the shutter open. The second way to do that is with a larger opening, and then you concentrate them down to a small point, like your pupil, or on a camera lens. That can happen too. So you might have heard of fast lenses. Those are just lenses that open really wide and then collect a large amount of light onto the sensor. Telescopes kind of do the same thing. They collect a large amount of light and concentrate it down to your eye. If your eye had a way to absorb light longer, then we would get even more brightness for the same amount of aperture. But the reason we can't do this is because our eyes are limited. The time that they're open to light, the chemical reaction, is very short. So about the best we can do without the aid of equipment is to let our eyes get dark adapted, and then look around, and you'll see a good fraction of this image, but you won't see any color, and a lot of these details will still be just out of reach of the eye. So let's look at this in more detail. So keep in mind this image. When you go outside and look at the sky, what we were just looking at is the Milky Way spread out across the summer sky. This is the Milky Way, our home galaxy, viewed from the top down. So this is us right here. That's our sun. We're so close to it as to not even register on the scale. It's just a single dot there in the center. And these different spokes, these different arms, are the constellation names that we look through to see different areas of the galaxy. So when we say the Sagittarius arm, we just mean we're looking through Sagittarius, and that happens to be where the galactic center is right there. And then in the winter, we have the Orion, the Auriga, the Perseus arm. They're all really dense and rich. But one thing that I always wondered when I was first learning astronomy is why is it that the summer, 180 degrees away from the winter sky, has rich, really expansive star fields and deep sky objects, but then in winter it seems just the same, if not more. But I've always thought, well, we're looking away from the center of the galaxy. It seems like it should actually dissipate or be less interesting than the summer side. Well, what's happening is there's the spiral arm that wraps around us here. And then there's also, obviously, I think looking towards the center makes a lot of sense because that's where everything's concentrated. There's much more activity there. But on the back side, we're still inside of this arm, so we're looking out through a very dense area as well. So on the right-hand side of the screen, this is just the pancake profile view of our galaxy looking edge on. So we're out here, kind of towards the outer edge of our galaxy. So most of it lies on one side, towards the center, but a little bit is still on the backside, but it's close to us and bright, which makes a big difference, which is why the winter sky, the winter Milky Way specifically, is very rich and in some ways preferable to the summer sky. I, for one, love the winter night sky. It's got so many rich targets to see. and you have the advantage that the sun goes down a lot earlier. Of course, it's cold, so that is kind of a deal breaker for a lot of people, very understandably so. Summer, you get much warmer conditions, but late sunsets, and so you can't always see as much, depending on your schedule. So it's just a trade-off between them, but they're both rich and rewarding in their own right. But this is what we're talking about when most of what we'll see through a telescope is going to be very close to us. So let's put some context here. This is not exactly to scale. This is just to get you kind of clued into the big picture. So the stars that are absolutely closest to us are the ones that make up the constellations. This is like looking at grains of sand that you hold in your hand on the beach versus the shoreline. Only the closest stars you can make out as individual points of light. Everything else just kind of recedes into this vast star field of indiscriminate points. It just looks like a cloud, really, in the same way that grains of sand up close look like individual little rock particles, but then when there's a lot of them, it becomes a large structure that you can't make out individual points. Same exact thing. So the constellations are very close to us. The next thing out is where we get these deep sky objects. These are nebulae, like the Orion Nebula. There's all sorts of star clusters, open clusters, globular clusters. These are really interesting areas to look at with optical aid, many of which, though, are visible even with the naked eye. You may not be able to make them out as points of light, so it might just look like a fuzzy little patch, but there's a lot of really cool things you can see out there. Most of those they tend to be on this side of our galaxy, but always within our galaxy. There are very few things that the naked eye can see that are beyond our home galaxy, but one of those is the Andromeda Galaxy, and it is 2.5 million light years away. The Magellanic Clouds, if you're in the southern hemisphere, are a little closer, and those are much larger, and you can view those as well. But most of what you're seeing is going to be right here in our cosmic backyard. Now, last thing I'll point out on the right-hand side, notice how thin the layer of stars is above and below us. So when you look at the Milky Way in the summer, you're going to see towards the center, this is towards the core, and this is the background stars as it recedes towards the outer edge behind it. But then above and below, left and right in this image, there's still stars, and those are just the stars on either side of this, like looking up and down in this frame of reference here. So those are just the ones that are closest to us, but it tends to be darker in those areas because there's not much in our galaxy between our view of the space above or below. It's just the stars closest to us that block it. But that's why the Milky Way is in a narrow band and doesn't wrap around us completely. So hopefully that gives a sense of three-dimensionality to it. I think that's something that is really important to keep in mind when you start looking for objects, because it gives you some really nice perspective. You're not just hunting down a faint fuzzy object through your telescope, but you're actually putting some thought with where that is and how close and far we are to these things, and it really drives home the I guess you'd call it the poetic side of it. Okay, so cosmic calendar. This is just a matter of perspective. Oh, question. Yep, bird is mine. Sorry. This is mostly just to put us in a timeline so we can understand how rare of a moment we're living in right now. I'm sure you've probably seen this before, but this is just the idea of taking all of time as we know it and compressing it down to a scale of 12 months. And basically everything interesting has happened in the last couple of seconds. We are just the last fraction of a second before midnight on this calendar. And this is the first time in our species history, but also all of known history, where we could have possibly known this about the world around us. So all the discoveries we've made from telescopes, all the knowledge that we've learned about physics and the world around us, this is knowledge that just was inaccessible completely before that. So I think it's a really important idea to hold in the back of your head as we look at all this. Just to appreciate the present moment and what we're doing and what we're capable of. If for no other reason than that, I think it's worth looking through a telescope at least once. So let's talk about how we got there. So up until, since antiquity, the Earth was presumed to be flat because the ground around you seemed flat. There wasn't a lot of easy ways to check that. Pythagoras, around the 6th century, started to suggest, I think it might actually be spherical. Aristotle promoted that idea further. Eventually, about 3rd century, a little before that, Eratosthenes did the experiment to calculate the circumference of the Earth successfully, and it's a very accurate value, especially considering the methodology. Um, and that was one of the main turning points when we started to get a little bit more understanding around about the way the universe worked around us. Still not very accurate. We still had a very geocentric model of not only the solar system but the universe. We didn't really understand that they were different things at that time. And then we have the heavyweights, Ptolemy, Copernicus, Kepler, and then we get to Galileo. Now, he didn't invent the telescope, but he did. He was largely credited with being the first one to turn it towards the heavens and make useful observations, and he recorded them in lots of detail. So he described the surface of the moon in as a kind of a three-dimensional texture and not just a perfect sphere with discolorations. So the craters and mountain ranges started to pop out to him, and he saw a lot of similarities with the terrestrial topography of the Earth. And prevailing wisdom was generally that the celestial bodies were perfectly spherical and smooth surfaces. He looked at Venus and started to see phases on it. And he had a very primitive telescope. This wasn't anything fancy. It would not be noteworthy by today's standards whatsoever. In fact, the little finder scope that you can find on really cheap telescopes is still, in many ways, preferable to what he was working with at the time because of manufacturing and technology advances. He also noticed the moons on Jupiter, the Galilean moons, as we call them now, in honor of him. So he started noticing that the world or the universe around us wasn't as perfect as he was led to believe, and the utility of the telescope was kind of made or popularized, I should say, by him at that point. When people started realizing that we can make discoveries around the world that challenge what we had thought up to this point, using relatively simple technology once it was finally understood. Now, on all the way fast forwarding up to the 90s, we have the Hubble Space Telescope. Now, what I think is most incredible about that, we're just talking about a span of roughly 400 years since the invention of the telescope till we launched one of the most powerful platforms in space we've ever had. People can live up to 100 years. We're just talking 4 human lifespans, kind of on the upper end, but just to make the point. That's not that long at all, especially when you consider the context in the cosmic calendar, going back to the beginning of the universe close to 14 billion years ago. Really incredible leaps have happened. And we are living in that moment now where not only do we know these things, you don't even have to have been the one who discovered it to take advantage of just the wonder and awe of knowing about the world around us. And furthermore, we have the technology and the economy to make telescopes available to essentially anyone who wants it. Even primitive gear is still very functional. So you can look around and replicate what these great scientists could have only dreamed of up to even a couple hundred years ago. So keep that in mind. It's kind of I'm not trying to sell you on a telescope if you don't want one, but I think it's just a really powerful point to consider how rare of a time we're living in right now. Okay, so let's go into telescopes themselves a little bit. A lot of times telescopes are marketed, unfortunately, with magnification as if it were the most useful feature of a telescope, and this is just simply not the case. On the left here, you can see an image of Saturn. Now, this is a simulated image at 70 times, 70 power, so 70 times closer. The light would look like that if you were 1/70th the distance away from Saturn as you are on Earth. You'll notice that it's very small in the center of the frame, but there's a lot of very crisp detail, a lot of clarity. You can see the ring structure a little bit. If you look very close, you can actually see the gap between the inner and outer rings. That's called the Cassini division. And it doesn't take up the full frame, though. That's one thing that a lot of people think is problematic when you're first starting out. You actually want a smaller view that's clear. It's always preferable to one like on the right, where it's simulated at 250 times, where it's big and blurry. Most of the color is spread out. What's happening here is that the limiting factor is the aperture, which you'll see much more in a second. But you can't get more detail out of it. You know how in movies when they're showing like a surveillance footage and they take a picture from space and then they say enhance, enhance, and then suddenly you're reading the date on a coin from 300 miles away. It's not realistic at all. The information has to be there, and that's a function of how much detail and resolution is carried on the wavelengths of light. And that is a nature imposed limit. There's no way around that. So you can't just put more power infinitely onto a telescope and hope to see more detail. More power is useful up to a point, but what happens is that if you reach past the limit of the optics, then you just see the image spread out. So in fact, here we're seeing um, the at most the same amount of detail as the image on the left, but spread out over a much larger area. You'll notice that it's very fuzzy. You can't even make out the individual details that you could in the smaller, clearer image on the left. Um, and it's pretty much useless. And in practice, it's very frustrating because if you put in an eyepiece that's that powerful and you try to find focus, the difference between focus blurry and out of focus blurry is so small that you really have no idea if you're even close. So a lot of people will think their telescope isn't even working. So the lesson to be learned is that magnification, you always want to start low and then build up. Um, a telescope's main functionality is its ability to gather light and concentrate it into a small area. So aperture, the opening size, is what really matters. That's really what we think of more as the power of a telescope. By analogy, magnification is kind of like the top speed on a car. It's really cheap to advertise a high number, but in practice you can't really use it except under very special circumstances, and it doesn't really tell you how well it's going to do going uphill with 5 people in the car. I mean, the power is what you really want. Magnification is a very secondary concern, and it has to do with the eyepieces mostly, not the actual telescope. So never buy a telescope based on magnification. If you learn nothing else, that is probably the most important thing to remember. So what does aperture do? Well, on the left here we have a 100 millimeter aperture, and then on the right it's the same image, a little bit more magnified, but with a much, much, much larger telescope. Now, you'll notice the big difference here. These are, I think the image on the right is stacked. It appears a little bit smoother than you'd expect, but the image on the left is what you'd typically see at extremely high power through a smaller telescope. This is well past the point of usefulness of that telescope. It looks very blurry and kind of underwater, and that's just atmospheric turbulence. And then on the right, roughly the same power, a little bit more, you can see a lot more detail because you're just collecting much more light, probably 5 or 6 times the amount of light, and then concentrating that down to the size of your pupil, which is very small. So not only you're getting more brightness, you're getting much more detail, and that's where our eyes really help us out, taking advantage of that new information coming in through the telescope. Okay, so let's look at a quick comparison here. This is the Orion Nebula. This is the constellation Orion. I'm sure you've all seen it. The three stars here in the belt, Rigel down here in the leg, and then the shoulder, Betelgeuse. This is the one that was fading last year, and people were really curious about that. Really interesting. If you haven't heard of that, you can check it out. So this is what it looks like to the naked eye. From a dark sky sight, you can actually see the nebula itself. It looks kind of pale and maybe a little bluish greenish. If some people can pick up more colors than others, it's just an individual thing. So this right here is the nebula. Then there's actually some nebulosity surrounding it on either side, but this is the main area. Now the next step up you go is a pair of binoculars. Now binoculars are not only they're useful in 2 ways to our eyes. One is that each individual optical element is larger than your eye by quite a bit, actually. It's roughly a power of 8 or 10 times more surface area than just the dilated pupil of your eye. So that helps a lot. But when you repeat that and have it with both eyes, you don't get a stereo effect, unfortunately. But your brain is so used to looking for stereo effects that it actually will sometimes create the illusion that you feel it's in 3D, even though it's not actually. The distances we're talking about are so vast that any parallax shift between your eyes is absolutely imperceptible by several orders of magnitude. But the brain wants to see that so badly that it will help kind of create it. And this effect is most noticeable actually on the surface of the moon, because there's so much depth information in the shadows as they're cast over the mountain ranges and craters that your brain is so used to seeing that it says, oh, okay, I know what that is, and I kind of want to see 3D so badly that it will really create the impression that it's three-dimensional. It also crosses between both. It will fill in some of the details between both of your eyes. So the final image that you're seeing is actually going to be clearer than either eye could see individually by itself. And you can test this out if you're skeptical. It's a really fascinating thing to see. But when you put it together, your eyes and then your brain fills in some of the missing details, and you create probably one of the clearest images you can get. And for that reason, I recommend always starting with a pair of binoculars. Or if you have a pair of binoculars lying around, give them a shot. Look at the Milky Way. The expanse of star fields just looks incredible in a way that you can't even get with a telescope because they offer a much narrower field of view. Binoculars excel at wide angle views at very low power with lots of light, and that's exactly what you want to see with the Milky Way. There's also a lot of nebulous regions, both in the summer and winter sky in the Milky Way, and elsewhere, some that are just above and below us in that plane, that are very interesting to see with binoculars, again, in a way that telescopes will show you more detail but a smaller image. So sometimes it's more preferable to have the bay window view, the panoramic image, than the more detailed up close views. So always a preference, but I like to have a pair of binoculars on hand for everything. There's never a time that they won't help. And then they're a great addition to a telescope if you do want to go that route. But it's a good way to learn the sky. There's so much you can see. There's a whole lifetime's worth of objects out there that are really great to study just with binoculars alone. So don't write them off too soon. The image in the center here is kind of simulated looking at the Orion Nebula again. So you can see some of these rifts and tendrils of clouds in the nebulosity. The stars here are basically sending light both through and scattering and reflecting it off behind. So think of car headlights driving through fog. The fog doesn't give off light, but you can tell it's foggy because of the way it scatters through the clouds. Same thing is happening there. And the reason we can't see a lot in between is because the gas, the nebulosity in between, is not quite bright enough or close enough to a star that sends light our way. So it's possible there is gas and interstellar material out here just like around those stars, but it's not bright enough to be seen. Now, when we add a telescope, this is where the advantage of aperture really starts to show. You can see so much more detail, and I am still impressed every time I go out to a dark sky and look through my telescope to see the Orion Nebula. It's the easiest thing to find in the sky, probably the most spectacular deep sky object, period. I try to look for new things because it's always fun to challenge yourself and see if you can check out something you haven't seen before, but I always return to this as my old favorite because there's just nothing quite like it. The view through a telescope, I can't fully describe it. This is close. It's one of those rare cases where it is actually better through a telescope than what you can simulate. Now, it won't quite look like the Hubble. You won't see color necessarily, those bright pinks and purples and all those different shades, but you will see so much detail, and it will cover the entire field of view, even at very low power. And when you understand that you're looking at a stellar nursery where stars are being born as we speak, as you're looking at it, it's an experience like nothing else. And you can see this even with the smallest telescope you can imagine. It's still even 3-inch aperture on up. It just gets better and better. And it's something that you can look at for hours and study and always see something new in. So keep that in mind. The three different tiers here, the naked eye, binoculars, and telescope, they complement each other. Definitely practice on Orion, but this is just one of literally hundreds of objects that you can find very easily in the winter sky. Okay, so how do telescopes work? Well, the basic physics doesn't change between different designs. We have the opening aperture. That really is the critical piece of a telescope. Now, it doesn't tell us anything about the quality, so this is where manufacturers do them differently, and there's all sorts of buying concerns, and we'll talk about that in our other program if you want to come to that. But just for now, understand the basic physics. Light comes in through the aperture, or the objective lens as it's called. It compresses it down to this small point, and then this here is where the eyepiece comes in. Now, the image from here never changes. That is a function purely of the telescope as you buy it from the store or whatever. Now, the part that you can control after that is what eyepiece you put in here, and this is where you control the magnification. So the magnification it's technically the focal length of the telescope, which is fixed, divided by the focal length of the eyepiece, which is variable depending on what eyepiece you choose to use. So you do have some control over it, though the baseline is preordained at the point of sale. So the eye is then taking all that light available and then concentrating just into the pupil. Now, there's all sorts of concerns about eyepieces too, because some very cheap ones will give you a pinpoint image that is completely useless. It's literally the size of a head of a pin, pen, and you can't, your eye is larger than that, so you don't get any benefit because you can't, your eye is larger and you're not seeing all the detail that it could be providing. Then the opposite can happen with some eyepieces that are so large and they're intended to give you a wide field view, but if it's too wide, then you have to move your eye around it to see the whole thing. Now, that's less common of a problem because those eyepieces tend to be expensive, and it's rare that you would accidentally buy something that expensive and not know that, but just keep in mind that that can happen, so it's worth reading up on eye relief and exit pupil and all sorts of other details. Again, we'll talk more about that if you're interested at our other presentation. Okay, so let's just talk briefly about the three main types of designs. The physics doesn't change. We're just doing it. The practice end of it is a little different. So the refractor is the most common, where it has a single glass element, sends it out the end. You'll notice they have eyepiece diagonals. That's this little piece right here, the mirror. That's mainly just for convenience and ergonomics. Often with a telescope, that's a straight tube. It makes you, if you're looking at anything in the sky, that means the eyepiece end is going to be low, and that can mean a lot of just discomfort trying to get your eye down that far. So the diagonal just sends the light back up at 90 degrees, so it's a little easier to see. It does invert the image top to bottom, and most of these designs will not be corrected for that, so you're going to have a left to right mirror image effect, which is something you'll need to get used to. And it's just weird. There's really no trick that I've found to work around that. If you've ever played with a telescope, you'll just get used to it pretty quick. Everything's going to be opposite of the way you think it should move. If you mean to go left, it's going to look like it's going right. But it's not that big of a deal. Your brain just kind of sorts it out. And also, when you're looking up at the sky at weird angles anyway, there's not a lot of reference to get used to, so you just get used to deciding, like, I'm going to go opposite and program my hands to move opposite, and it works pretty quickly. A reflector accomplishes the same task, but by using a mirror instead. So the primary objective, instead of being at the front end of the telescope with a piece of glass, it is actually at the back, and it is just a mirror that then converges light onto the secondary mirror, bounces it out here. So you'll notice it has two elements instead of just one. So it has that embedded secondary diagonal, so to speak. And this is where the eyepiece is, and then the eyepiece is the only interchangeable part on any of these designs. The third option is kind of a composite of the two. It takes light in through an opening objective glass element, so this is a lens, sends it to a mirror, sends it to the secondary mirror, and then out through the back. And there are some benefits to both. So just really quickly, a refractor is the kind of design you're used to seeing as kind of the stereotypical telescope. It's just what we talked about, where the light comes in, it's concentrated out through the eyepiece. Really not a lot of fancy things in that. They offer, they tend to get expensive as the aperture goes up, so you won't see very large ones. They go very quickly, actually, as you up to about 4.5, 5 inches. Anything past that, and it becomes almost an observatory grade equipment. Very hard to find well-produced lenses that are that large. They offer typically the highest resolution per inch. So if you have two telescopes that are both 4 inches in aperture, let's say, the refractor will probably give you the slightly better view. It's going to give you just a little bit more detail and resolution in the way that it handles the light. Let's look at a reflector, the second kind. This is very similar. It just comes in through the back, hits the mirror, and then bounces off through diagonal and then out through the eyepiece. Now, these have slightly lower resolution per inch than a refractor, so the advantage with these is that you can get large apertures at relatively affordable prices. This is a 10-inch reflector. I don't know that I've seen any amateur-grade 10-inch refractors that are made of glass, but a reflector is not that cost-prohibitive at all. You can find entry-level models for $500 to $800 typically in this aperture class. Now, notice that 78.5 square inches is being concentrated down to your pupil. So that's a huge increase in the amount of photons concentrated on your eye, and which, again, is what we perceive as brightness. So this will be great for looking at faint objects, deep sky objects, nebula, galaxies that are outside of our own, star clusters, all sorts of interesting things. But if you do want to look at high resolution views of the planets or the moon up close, you can still put in a fairly high power eyepiece and achieve that, although a refractor will probably be preferable for that. So lunar and planetary is better for refractors. Deep sky object is typically better seen through a reflector. The third option is a catadioptric or compound telescope. Um, these are kind of a composite. So, like I said, they use a lens at the opening end to concentrate light onto the mirror and kind of pre-focus it. Then the mirror sends it to the secondary mirror and then back out through the tube. The advantage is that the focal length is very long. It actually, because of the light path going back and forth a couple times, it multiplies the effective focal length. So this telescope would be somewhere around 3 or 4 feet long in terms of the length of the optical path, but it's collapsed down into just over a foot in terms of physical dimensions because of the way the lenses and mirrors are folded in. This is about 7 inches in aperture, and that gives you 38.5 square inches, but the resolution per inch is higher than you'd get with a reflector. So you get a little bit of both there. It's very large aperture, though not as large as a reflector for the same price, but you have the advantage of having more resolution per square inch, and you can use higher power and still get some clarity out of it. So it's a good option. They're very portable. I recommend them if you're starting out. There's really no way to go wrong with them. No moving parts for the most. The mirror will focus back and forth, but you don't have to worry about collimation as much as you would, or alignment of the mirror as much as you would with a larger reflector, which does have to be periodically collimated or have the mirrors aligned just to make sure the image is as crisp as it can deliver. Okay, let's look at the animation real quick. So you can see it just comes in through the front, out the back, through the mirror, and then there's this secondary mirror. You can see in the picture here, it's kind of glued actually onto this objective lens and then goes out through the back. And this corkscrew focuser is the only thing that will move on it, but it is designed to be aligned at the factory, and most of these don't offer a way, because they don't need it. They don't typically need to be realigned ever. Most of the alignment issues happen at the front end. So a reflector, you'll have to align that secondary mirror every now and then, make sure that the back mirror is sending the light directly to it, and then that the secondary mirror is sending it out to the eyepiece. These typically are easier to handle than that, and they're smaller, so they don't endure the same kind of bumping around when you're transporting them, and they can fit in an airline bag, and you can carry them with you. And if you're interested in daytime use, like bird watching or just using it as a spotting scope out for like in the mountains or something, they work great for that. You can put in a special diagonal. These are 90-degree diagonals, so those will invert the image top to bottom, but you can actually get a special 45-degree diagonal that will invert the image both top to bottom and left to right mirror image, which restores it to the way your brain is expecting to see an image. So everything that you see is right side up, left to right, correctly oriented. So you can use it for bird watching and it will make sense. You're not looking at upside down birds or something. So keep that in mind. Let's move on. Okay, I mentioned eyepieces earlier. Eyepieces are the most commonly overlooked piece of a telescope. There's a lot to consider, so I'll just say that the number on the side, if you happen to have one and you're curious what it does, the number is the focal length, and it's usually listed in millimeters. 26 millimeters is the most common bundled type of eyepiece. Generally, with most department store telescopes, I would recommend replacing it as soon as possible, because usually the telescope is better than the eyepiece that it came with. They're hard to manufacture well, and that drives up the price. And so from a marketing standpoint, they typically want to give you the cheapest telescope they can, but still fulfill the whole kit idea and give you something so that it's at least usable out of the box. I kind of wish they didn't do that, because most people don't go out and buy a second eyepiece after that. It's always worth it. We'll talk about how to do that again. There's a lot more than I can really condense down to just a few seconds here. But the thing you want to keep in mind is that the opening at the end where your eye actually looks needs to be large enough that your pupil can see around it. So you don't want those little tiny pinprick little holes, kind of like these ones over here, if you can see my cursor on the far right corner of the mat. Those are starting to get so small, and that happens on the smaller end. So these are the lower numbers, like probably a 4 or 6 millimeter eyepiece, I would guess. They start to make them the part where your eye looks into so tiny that it's not helpful. You're not getting any useful detail passed onto the eye. It's just a little tiny slit that you're looking through. On the other extreme, you have these larger eyepieces that give you that bay window experience. Now, the glass is wider than your pupil is, but the actual image is just handled in the center of it. A lot of this is just for color correction purposes or final focus correction. So the different colors of light, which are all a different wavelength, they tend to focus at slightly different planes, and there's very fancy optical techniques to correct for that and consolidate them into a single plane. So when you look at it with your eye, you see all the focus or all the colors coming together perfectly in one image. Cheaper eyepieces will have what's called fringing, which is where you usually will see blue or red around the edges. And what's happening there is that they just optimize the eyepiece, usually for green because it's in the middle. So red, orange, yellow, green, blue, indigo, violet, colors of the rainbow. They just pick the one in the center, which is the brightest to our eyes, let that focus, and then the red and the blue suffer the most. So they're actually focusing just in front of or behind the plane that your eye is looking at, and that's what causes that fringing effect. It's a lot more complicated and therefore expensive to correct for, but many eyepieces will do that, and they're becoming much more affordable than they used to be. If you're interested in this, definitely reach out to me. I can connect you with some good resources, and there's a lot of good eyepieces that are not too expensive that do a very good job of basically compensating for all the major areas. So the pinpoint stars across the field of view, mostly fully color corrected, and wide enough exit pupil that you can see everything, but you're not faced with like those little tiny pinhole views or too much information that your eye can't take in because it's just for marketing hype. So eyepieces are their own area. Just keep in mind, if it came with it, it's probably just a paperweight. Just go ahead and get rid of it. It's not worth anything. There's no resale value. You'll want to replace it. Mounts are extremely important, and there's a couple different kinds of them. So I'm just going to say for general purposes, most mounts won't have tracking built in. A lot of these new department store type telescopes will have some sort of computer control which simulates the effect of tracking. If they work, which is a big if, that will be better than nothing. Generally, I found that they don't, their alignment procedures are not very helpful, especially to beginners. So let's just talk about the two big types. There's equatorial mounts, and then there's basically everything else. So equatorial mounts, these are, or German equatorial mounts sometimes, you'll see it abbreviated in marketing literature as GEM. These are the kind that compensate for the Earth's rotation. So that's what I'm showing you here, that you can see the counterweights on the left, then the payload, this is the optical tube assembly, this is the telescope part that you look through, that sits on the other side. And then there's this big cast iron metal mount. You can already tell by looking it's going to be very heavy because however much the telescope weighs, you have to have at least that amount counterbalanced on this side. It doesn't necessarily have to be the exact same weight because you can control the distance and so the moment arm, but it's going to be close. And then the mount itself is, in this case, this weighs about, I believe, 35 pounds, somewhere in there. It's not light. And it takes a considerable amount of time and effort to set up. It takes maybe at least half an hour to get it from everything in the box to out and running. And then you have to have it aligned reasonably close to north for it to be helpful. If not, it actually will work very hard against you. So this is more if you're into it for, if you like high-powered visual observing, or if you're into astrophotography. In my case, I like this because when I'm doing public outreach, it's really nice to be able to put a high-powered view of Saturn, but if I get reasonably close to north alignment, then I can let it track for about 10-15 minutes, even if it's not perfect, then it stays in the center of the eyepiece and it doesn't drift out of the field of view. So that means if you have 100 people waiting to look through it, you don't have to stop and recenter it each time. And then it also locks down pretty tight, so if, like, a kid looks through it and bumps the scope, chances are it won't go out of field of view, or if it does, it's still pretty close, so we can get it up and running pretty quickly. These are not necessarily beginner friendly. You can get them, and if you're interested in a challenge, I would definitely recommend it. There's a lot of resources now that make it easy to start in a way that when I was starting, I got so confused with the manual and couldn't figure out how the thing was supposed to work at all. So just keep in mind that it is a little steeper of a learning curve, but you have the advantage that it will track the night sky either with a slow turn manual cable or an electric motor of some sort, even if it doesn't have a computer. So that can work for you, but you have to work for it first. The other types are the alt-azimuth mounts. These are just the ones that are pan and tilt. They just go left and right on the horizon and then up and down towards the zenith, up from the horizon. Now, these are great for most purposes. Some of them have tracking where they actually will have two motors now instead of just the one like an equatorial mount. Two motors where one will go left and then one will go up. And the reason is that things across the sky move in an arc. So it's not just left to right or up and down, but you actually have to have two components of motion. So you have one motor going left to right and the other one's going up and down, depending on what you're looking at and where it is. So it can be done. They're not as helpful for astrophotographers because what they don't do is rotate with the sky. So as an object moves across like this, it might be tracking the center of it, but it will appear to twist around the face. So then you have to get what's called a field derotator if you really want to do that. This design on the right, it's a Schmidt-Cassegrain. I believe it's a compound telescope. So you get a very large aperture and very high power because it's compact and the light path goes over a very long distance. So you can get high magnification pretty easily. There are people that use these quite often and regularly for astrophotography, but you have to you'll notice it doesn't correct for the tilt. So you have to have both motors going and then have that field derotator literally twist the frame of the camera in it in order to prevent that rotation from smearing the image. There are ways that these can be mounted on equatorial mounts, but then it just becomes a matter of how much hardware do you want to carry out in the woods with you every time you do that. A lot of people will actually buy these and pier mount them permanently, like pour a concrete base and then have a fixed pier in their house or observatory or whatever they have, depending on your level of engagement with the hobby. But some people do that for sure. And then they will just polar align it once and get it as close as they can and then do the rest with software so that way they don't have to move it from night to night. Dobsonians are probably my favorite recommendation if you don't have any clear idea of what you like. The two main categories of visual observing are lunar and planetary on the one hand and then deep sky on the other. Personally, I do like deep sky. I just think it's really interesting to see these really faint objects when it might just look like a fuzzy pale patch, but when you know that that's an exploding star that's moving just beneath the level that our eyes can see, it's really fascinating, and I kind of enjoy that. The planets never get old, but you can always use a telescope that's suited for deep space, deep sky observing. It will still work on the planets. It's just maybe not as pristine and clear for the same resolution. So it'll be close unless you really want to get into visual observing of very tiny details like storms on Jupiter or sometimes on Saturn, or splitting double stars, which is a whole area of specialty, even at the amateur level. I would recommend getting a reflector on this kind of mount. A Dobsonian mount is the Lazy Susan style that just spins. It's a pan tilt mount, but it rests on the ground. This whole telescope design is just one single piece. There are no detachable parts. Now you can remove them from the base if you want to transport them, but some people just carry them as this. It just sits in that little cradle on the base, spins around left to right up here, then tilt is handled up here. Instead of a counterweight, it's mounted very close to the center of mass, and then there's these tension springs that will help you balance whatever eyepieces you put in. So if you put in a really heavy eyepiece, you might add a little bit of tension to correct for that. But they're very easy to use and very easy to get started with. You can get these for $400 to $500 entry level. They'll show you everything you could possibly want. I would recommend starting with a 6 or an 8 inch if you're going to get this design, just because they're cheap enough that'll give you so much room to grow into the rest of your life. They're portable. Now they're starting to make some of these designs that are collapsible, so they sit on a truss frame that will not a truss frame, a telescoping frame on a telescope, where you just unscrew it and it collapses down to half the size, and you just put a shroud over it or something to block off-axis light if you want. But they're becoming much more. They've always been very popular and very cheap, and they're just getting more so these days. So I highly recommend these for any entry-level purchase. Now, computer control. Almost every telescope you find in especially the department store variety, the kind that get a lot of advertising and marketing hype, they're all going to have computer control of some sort, typically speaking. And I don't recommend that for the most part. Now, it is nice to have electronic control of the motors, so if you do have a motorized mount, you can just press an arrow and it will slew for you. There are advantages to that for sure, especially when you're trying to find something at high power and you get close, but then when you touch the telescope to move or do anything manually, the vibration from that can cause the image to wobble so much that you can't see anything for a second. You have to like do a small adjustment, wait for it to settle down and dampen, and then look through it and see how close you are. Um, a computer control can help with that because it can give you extremely slow slewing speeds that just let you fine tune it with the motor and not your hand. So that's helpful. But the alignment and auto tracking and go to features, they don't really work unless you already know what's in the sky in the first place. So you kind of have to know what it's looking for. So when it slews to Rigel and says, "Is this star centered in the field of view?" If you don't already know where that is or have some sort of external reference, it probably won't help you to have the computer guessing. And I can tell you from experience that they don't always work correctly out of the box. I've helped several people set these up over the years when we do our in-person events, and they're disappointing for how advanced the technology could be, even at that price point. But they usually will make a bad guess, and then you'll have to correct for that, and then it's hard to explain. Well, it just would have been faster if you looked up how to do it in the first place without the computer trying to help. So, but let's just say the computer does work. You finally get the alignment to work, and you enter M42, and it takes you straight to the Orion Nebula. Um, it also took all the fun out of that process. You don't know where the Orion Nebula is necessarily because it did all the driving. So I call it autopilot syndrome. It's doing all the work for you, and you're just along for the ride, but missing most of it in a way. So I think it's better, especially when you're getting started, just learn the sky from a star chart in a traditional way. It'll stick with you a lot better. It'll connect you more with the experience, and then you can also recognize, like, every time you're outside at night, you can just say, "Oh, I know that constellation. I know what's in between those two stars there," because I recognize the pattern from having struggled with it myself, rather than letting the computer take me there and then I just look through it once and then I'm done. So to save yourself the headache and simultaneously get more out of the experience, I highly recommend avoiding computer control. If your telescope does have a computer, don't worry about it. You can also use the manual mode. Mine, for example, does have the computer control in it. I've never even tested it out. I've learned on other telescopes that I just hate it, so I just use the manual control. So they just power the motors, but they don't actually take me there. So I get to do the driving and tell it where to go, and I'm comfortable with that because it's easier. Um, so common mistakes when you're buying a telescope, of course, we talked about the different types of viewing, like planetary and lunar, deep sky objects. But there's so many different designs out there that you want to factor in what you're interested in seeing. So between those two categories, even if you don't know, that's fine. But you might want to just say, I'll get a telescope that can do both. And then you can decide later, and maybe you don't want to specialize. You want something that can handle both relatively equally well. Um, the other factor is portability. So the tracking telescopes are going to be heavier and more time consuming to set up. The Dobsonians won't have tracking, but they will probably give you a very good view. They'll force you to learn the sky, and they're much more packable and durable, so you can take them more places. Um, you'll also want to consider if you're interested in kind of going the long route, where you want to expand gradually over time, or if you just want to get an entry level and keep it there, or if you want to buy one that you can grow into over the years. That will drive up the price a little bit, but it also may be cheaper to do it that way. If you know that that's your interest and you're committed to it, it'll save you from buying two, one at the entry level and then one that you really want later on. And you'll also, of course, want to replace the eyepiece that it comes with from most companies. There are a few exceptions to that. And then obviously ignore the marketing hype and all that. And I recommend talking to people. There's always somebody who's bought that telescope before. So if you wanted to see how other people have enjoyed it or not liked it, you can look online and find that, or you can call up. Like here in Denver, we have Mile High Astro. There's a couple other nation-wide service centers or retailers that will give you great info. They've been doing it there for many, many years. And so they'll give you a lot of that insider advice that you can't get even from the manufacturer typically. So talk to people, make it an investment that you're interested in. The important thing to keep in mind is that the best telescope is the one that you actually use. So even if you have an unlimited bank account and you want to buy the nicest telescope you can find, that doesn't mean you're going to have a good experience with it. If it's too complicated or too heavy or just got too many things on it that you don't really care about, it's not going to get used as much, and that's robbing you of the experience. So I recommend getting one that you think is going to be suitable for what you want in the short term, and then give yourself room to grow if you want. But the one that is best is the one that's used, and that's different for everybody. So one other thing to mention is that these kind of telescopes that you see like at Walmart, Target, any of the major retailers, they're nicknamed pejoratively department store telescopes. They have a lot of flashy marketing. This one is only advertising 18 to 60 power. Most of these that I've seen in person will offer like 500 or 800 times. And while technically maybe the eyepiece that they came with them, if you did the math through the formula, take the focal length divided by the eyepiece focal length, it might come out to something absurd like 500. It might be able to do maybe 100 max, both even on a perfect night and if you have everything optically perfect. They often over advertise everything. They're a disappointing experience. They use very irrelevant marketing tactics. They're cheap, flashy, unethical. I call them the Johnny Cochrans of telescopes. So steer clear. Okay, so professional astronomy. Let's just cover really briefly what's out there. So this is at the amateur level. This is what you could buy without getting a second mortgage or something. Professionals do a lot of the same things, but they do it in very different ways. So the basic concepts of gathering light, concentrating down to a small area, that still holds true. But the types of objects that astronomers are interested in are not just in the visible wavelengths. It's interesting, too, that what we think of as visible light, which is the range of wavelengths that our eye can detect, we see colors, but color actually isn't a real fundamental concept in nature. It's more of a neurological interpretation of a physical phenomenon. So it happens in our brains, not in nature. Now, it's not that the wavelengths of light don't happen. They absolutely do. It's just that the color red is not a universal term. It's just how our brain and our eyes interpret that particular wavelength of light. So when we go to the next step up, this is a picture of the Keck Observatory in Mauna Kea in Hawaii. A lot of professional observatories are built very high above the ground, and there's a couple of reasons for that. One is that they get above a lot of the weather. So as we all know here, if you're trying to look outside, if there's something like the conjunction happening or Mars is reaching opposition, Murphy's corollary for astronomers is that it will be cloudy that night, and probably only that night. But to get above a lot of the weather, that gives you better odds of seeing through to the sky. So that's good. But the other thing that's important is the wavelength that you're looking at. Now, some things that are just going to be intrinsically deficient with ground-based telescopes so that you can only see what happens on the night side of Earth. And that makes sense because we can't see through the sky during the day. But at night, that might not be the time, or the Earth side, sorry, the night side of Earth, the shadow of Earth, may not be looking at the object that you want to see if it's a very timely event. So let's say there's a supernova happening. We can't see it if it happens on the day side of the telescope. So there's an intrinsic limitation, and you can't get an exposure of an image longer than the amount of time it's in the night side of Earth. So that is one issue. The other thing is seasonal limitations, that you can't see on the other side of the sun. So there are certain parts of the sky that are just completely off limits at certain times of the year, which kind of makes sense. Let's talk a little bit about the wavelengths of light. So this is the Milky Way in different wavelengths. This is going from long wavelength to short wavelength up here as we go down towards the bottom. Optical, this is what our eyes would see. This is just the edge-on profile view of the Milky Way. But you see, there's all sorts of different information visible in different wavelengths, and that is really important to astronomers. So when we start building big observatories, one thing we have to ask first is, what will this be observing? And you may be surprised to know this, but most observatories don't spend a lot of time looking at visible light objects. They actually spend a lot of time in the infrared or some of the radio waves, but they certainly do optical work, but not as much as you would probably imagine. Now, one thing that happens with the atmosphere is that it exponentially decays in density all the way up to the edge of space. So when you start at the ground, the air is breathable, there's enough pressure, but then as you go up, it drops off quickly up until the Kármán line, roughly, and then there's just average collections of molecules, but we don't consider that atmosphere above that point. Um, and what happens inside of that is that light is scattered and absorbed. And so the denser the air is, closer to the surface, the more light is affected by the atmosphere. Now, this is why the sky turns blue. It's called Rayleigh scattering. And basically, the thicker the atmosphere is, the more it subtracts out the shorter wavelengths. And blue is the shortest wavelength. So the thicker the atmosphere, the more that blue gets pulled out. It can't push very far through it. So during the middle of the day, the atmosphere is very thin because that's the shortest amount. If you think about like the atmosphere wrapping around the Earth and the sunlight's coming in above, that's the shortest distance the atmosphere has. But as it moves towards the horizon where it gets longer, now the light is coming in from the side, and most of the blue light gets scattered and kind of subtracted out of the total image. And the longer wavelengths aren't as affected by this, so they make it through further. So that's why you see it go from blue, and then as we get towards evening, it starts to get yellower and then deep red right before it sinks below the horizon. This effect, though, happens with other wavelengths as well. So this is one of the reasons we developed things like the Hubble Space Telescope, where it's able to get above the atmosphere and therefore avoid all of this. So this chart shows you the different wavelengths of light and the windows that are opaque to the atmosphere and wavelengths that aren't. So there's a radio window. We can see the optical window mostly. Very little infrared gets through, but some gets through more than others. And then as we get shorter and shorter, almost all of it is blocked, and it's completely useless to try and study from the ground. So this is why there's a limit to how many observatories or how much we can see at higher altitude. While they're able to get above a lot of the atmosphere, they're not able to get above all of it. NASA even launched a program called SOFIA, which is an airborne telescope. It sits in the back of a converted Boeing, and they cut out the back so it opens at very high altitude, and the telescope's mounted on a stabilized platform, and it gets above enough of the atmosphere that you can do some useful infrared astronomy above the atmosphere without the cost and maintenance of trying to develop a satellite that flies on its own outside of the Earth. So this orange little window here is Hubble's viewing range. It goes from the infrared to the ultraviolet and then the visible. This is what that looks like. We're showing two separate images here. These are kind of different I think these are the pillars of creation, actually, or a segment of that image. But this is what it looks like in false color visible light, and then this is the same area imaged in the infrared. Now, if that image were attempted in Earth's atmosphere, essentially nothing would show up. You would just see maybe a few of the stars because they're emitting in the visible light as well, but all this interesting detail in the nebulosity would not come through. You just see emptiness or black space, basically. So this is the area that it's looking kind of near infrared and then ultraviolet. The Hubble Space Telescope is very fascinating, both the physics that it's produced and our understanding of cosmology, as well as the engineering that goes into it. But fundamentally, it's not that different than even your typical backyard telescope that an amateur could have. Light comes in, hits off this big mirror, bounces off the secondary mirror, then into the camera, and then there's four main instruments in here that, depending on which one is looking through it, it will show you light in a different wavelength. In the interest of time, I think I'm going to skip this, but if anyone wants to, maybe I could give you the link. Here, let me put this in the chat. It's really good. I'm going to just show you the image of the Hubble Deep Field. If you want to watch a brief overview, I'd recommend it. It's only about 5 minutes long, but I think we'll just keep moving for now. This is the image that it produced. They basically, there we go. They basically imaged an area of the sky where they thought nothing was visible. So they were not expecting to see anything, and this was kind of a what if scenario. So there was a cumulative exposure for about 28 days that found 3,000 different galaxies in this. Now remember, before this image was taken, this patch of the sky was considered completely empty. There were no known targets of any sort, no objects in that field of view. And this is kind of a galactic core sample. We're looking at things both very close and very far away. So these galaxies that you see up close, that's the same thing that you're seeing just way off in the distance as the average size shrinks as distance goes further away from us. So really cool. There's so much science that has come out of this image. They've repeated this multiple times. So there's actually more than one Hubble deep field. But this is one of those things that I think it's just really important to take a step back and consider that, again, 4 human lifespans back, we were at Galileo, and he was kind of scratching his head as to why the surface of the moon seemed to have depth. And then here we are probing back to an almost the earliest visible light in the universe in this single image. That's a very short amount of time to have made such strides in our understanding of the world around us.
Aric, can you
So
hear
let's look
me?
at, yeah.
Diana is asking a question, I believe, on the previous pictures of the nebula. She's
Oh,
asking, are those pictures edited to see more details on the light?
oh, on the deep field image, I'm sure they are. Typically, what they do is they take the light. They usually, I think the camera on Hubble for this is only able to see one color at a time, and I believe they do multiple passes. So they'll take it in red, then green, then blue, maybe with a filter or something to let the only that light kind of screen through on the detector. Um, and then they'll combine that. So they have all sorts of imaging techniques that they use to get the image out. Typically, though, the images from Hubble will be in false color, and that happens when they're taking images. And I should look that up. I don't actually know off the top of my head uh, if this is strictly visible or visible plus something else. When they have multiple wavelengths, what they'll do, if it falls outside, so this is your visible light, if there's infrared or UV on one side, our eyes can't actually see that. So even though the detector will register a signal there, our eyes don't see that, so it can't reproduce it in that wavelength, or else it's invisible. So what they'll do is they'll compress it, and they'll basically say, they'll look at a color wheel and assign the infrared a color that isn't used elsewhere in the image. And so if everything else is red and green, let's say, I'm just making this up, they'll make it blue, and they'll assign a blue value for the infrared and then mix that in. And then they'll do the same thing for the ultraviolet or the non-visible spectrum wavelengths. And then they'll create a false color composite, so that way we're seeing the detail captured outside of our visible range, but compressed into the visible range so our eyes see it. So even if you had, like if our eyes were somehow sensitive enough or large enough to see this far, like at the scale and power of the Hubble, we wouldn't register the same color unless we had somehow extended our range of vision outside of just what we call the visible lengths. So I'm sure they do a lot of that kind of processing. Then there's also just the boilerplate contrast and luminance effects, where they just basically take the faintest part of the image and then the brightest part of the image and try and widen that so you can see more detail. A lot of the images, I haven't seen many of them from Hubble, but from many observatories, or there's the Juno cam, which is orbiting Jupiter right now. It's it does daylight imaging mostly, so not long exposure. But when you get the images from these telescopes, they usually don't look anything like the final product. And so I'm guessing on this, but I'm imagining it must be very comparable. It'll be basically flat. Like the image, at first it'll look like nothing got captured, but then when you start teasing out the details and stretching the dynamic range, that's where the image starts to come to life. And from what I understand, that process is very similar with how amateur astrophotographers will capture images. Some of the most stunning imagery I've ever seen, thanks to the internet now, you can actually watch some of these guys. They'll generously share their raw plates and then compare it to the final product. And I was amazed the first time I saw that, and you really can't see any image or anything registering in the first raw plate that they download from the camera. And then through a lot of complicated imaging techniques, they'll use Photoshop and some other specialty tools. They'll stretch the dynamic range, add contrast, make the grays black, and then the lighter grays white, and then they'll get all sorts of color to tease out and all sorts of detail that is technically there. Excuse me. It's just not visible to our eyes originally. So I haven't seen any sort of raw images for this, but I'm sure that something has been done to it to make sense of it. But they would never add anything that wasn't there. So what you're seeing is representative of that part of the sky, meaning there's no, they didn't like add in any galaxies or anything like that. All that image, all the detail was captured from the raw plates, but they may have artificially enhanced that to make it similar to what our eyes might see in a simulated sense. Okay, so just to highlight, I'm not going to go into these images, but these were just taken last year. This wasn't that long ago. This is Jupiter and Europa here in our own solar system. Hubble is past its originally intended or planned lifespan. It's alive and well, taking really cool pictures, and this is one of them. This is last August 2020. It discovered these vortices on Neptune last December. This was taken last July 4th of all times. It's really, really cool to see. You can actually see very slight hint of the hexagonal structure in the poles. That's kind of a recent discovery. There's some other really cool pictures. I think Cassini has some of the aurora, basically the charged solar particles interacting with the atmosphere on the poles of Saturn. And you can see the hexagonal shape up at the top, which is really fascinating by itself. I don't quite understand why that is, but I'm sure the information is out there. It's just a matter of looking it up now. And then you can see basically what amounts to something similar to lightning, or a combination of lightning and aurora happening on the poles of Saturn. We can't see it in this particular image, but the shape is there. Also, these bands on Saturn, you might be able to see two of them through a telescope. So let's say we do this next year, and I have my telescope set up after we talk. I could show you probably two of these bands. Hubble can see obviously much more because there's no atmosphere to distort any of the images. It comes through completely unencumbered by atmospheric scattering. If you're interested in these images, I'm just going to skip through these. There are so many more of them on Hubble's website. It's impossible to keep up with them. If you go to the Space Telescope Science Institute's website, they have a gallery of unbelievably wonderful images, and they're updated regularly. I was surprised to know when I was putting this together that so many of these were taken so recently. I kind of, in the back of my mind, thought maybe 5 or 10 years ago they quit taking images of the same things. But no, they are constantly getting new images, and they're getting better and better. And on the other side, on the ground side of things, as computational imaging techniques improves, they're able to apply new processing methods to old data. And so there's been some interesting examples where they take an original image from Hubble, then reprocess that data using the newer methods, and they get a completely interesting image that doesn't, I mean, it looks like the original, but it looks like it was taken with a completely new camera. It's gotten a complete facelift. This is the Andromeda Galaxy. This whole image is, I think, close to 5 gigabytes if you want to download it. This is a patch or a mosaic of a bunch of really tiny images stitched together. This video just shows what that looks like up close. Now, what I think is most interesting about this is that, remember when we're looking at the Milky Way from the inside out, most of that is going to be background stars, but when we look at Andromeda, we're actually looking out through our own galaxy first. So all the big bright stars in the image, those are here. Those are our stars in the Milky Way. Those are just in the foreground. Then the Andromeda Galaxy stars start to appear at a much, much smaller level because the Hubble does have the resolution to make out individual points of light, even at that distance, 2.5 million light years away. So these bright stars are here in us. These are like looking through the trees and then seeing the forest behind it. All these, now we can start seeing individual stars in Andromeda. So really cool thing to see. Wouldn't be possible from a ground-based telescope. And then here's a supernova image captured by Hubble. This is a comparison before and after of the same area imaged twice. Supernovas are when a star dies. It's just really rare to capture one. And Hubble is reconfigurable very quickly, so we were able to detect it and then move the Hubble up to it. The engineering behind it is a whole other interesting discussion sometime. This is just another galaxy nearby, very similar to our own. You can see the spiral shape. It's just really fascinating to see this as a non-simulated image of those things that we were talking about earlier. Here's two galaxies colliding in very, very slow motion, but they're gravitationally intertwined and entangled, and they're ripping each other apart as they reform. And we can see various stages of this behavior as we look at different galaxies other than our own. We can see some that are edge-on and some that are completely flat. And we see them at different stages of their interactions, and astrophysicists use this as a reference to build models that predict the behavior of galaxies over millions of and billions of years, because we just don't quite understand the dynamics of how that happens. But when we build a model, we have all these data points spread out through or through our universe that we can see at different points in its life, and then see how closely our models track to that. One really interesting phenomenon when galaxies pass through each other like this, and nobody really understands quite why as of now, the stars never collide with each other. So you have these two masses that pass through each other, but they don't have any impact with that, which is a really interesting thing, and they're still working on that. So a lot of new science is yet to be done. And then lastly, this is the famous Pillars of Creation, the Eagle Nebula. This is something you can see with a pair of binoculars, and I highly recommend you check it out. This is more of a summer sky object. It's named the Eagle Nebula, hopefully for obvious reasons. These are the talons here, this is the head, these are the wings. You can see this in visible light with a pair of binoculars. It's kind of tiny, but it can be done. With a telescope, this really comes to light. Last summer, I remember looking at this out. I can't remember exactly where it was, but it was on the far western side of the state. No lights anywhere. I was up all night with it, and it finally peeked through the trees, and I got to see this. Best view of it I've ever had. It's really close to a spiritual experience in the more literary sense of that, but it's really phenomenal to see. And this is what it looks like when Hubble looks at it with false color imagery. Now this is like I think on the very first slide, or further back at least, it showed how it was showing visible versus infrared. This is a composite of both of those, but this is nicknamed the Pillars of Creation, and that's not just kind of an allusion to a biblical thing, as much as it is a very objectively true literal statement, because nebulae are where stars are born. They're the stellar nurseries. So these clouds of gas and dust will eventually reach a size and scale that the heat and pressure of their increasing gravity will collapse on itself, initiate the fission reaction, and in enough time a star will be born and we won't see those clouds anymore. So we live at an incredible time to be alive, whether it's through the internet or through in person or however. Go look through a telescope. I think you'll be very glad you did. That's all we have on telescopes for now, and if you have any questions, I'm happy to stick around. I'll just mention that if anyone's interested, this week we're going to be doing our Wednesday program on bad astronomy. It's about the closest I get, at least on the public side of our group, to a skeptics debunking thing. We're going to be looking at claims of the flat Earth, the Illuminati controlling everything, and the moon landing being faked, and all sorts of interesting claims based on Phil Plate's book and Carl Sagan's Demon Haunted World. So if you're interested in that sort of thing, join us. It's totally free, 6 o'clock this Wednesday. And you can see all of our other programs up at StanleyStargazing.com/events. Thank you so much for having me. I really enjoyed this, and I'll open everything up for questions, and stick around as long as you want.
Thank you, Aric. I asked everybody to unmute if you'd like to ask a question.
Yeah, thanks, Aric. That was really good.
So
go ahead.
Sorry, go ahead, Tom.
I was going to say, so if you're on a budget, but you want to get something that's decent, how much do you have to spend? I mean, what's the minimum they have to spend to get something that's worthwhile, as opposed to a department store?
Yeah.
Telescope.
I just put in the chat. Oh, sorry. I thought you were done.
Oh, that was pretty much that. I mean, I've looked at some of these really cheap telescopes, and they're just, like you say, they're not really, getting a lot of value. So that's all.
What I recommend is Orion telescopes and binoculars. You really can't go wrong with them. I'm not affiliated with them at all. I really love what they do. What sets them apart from most big box manufacturers is that companies like Meade and Celestron, you've probably heard those if you've been in the market at all. They're the two big players. And then there's a couple others that are coming online, but those are the big guys. They have basically two different worlds. They have their legitimate gear, basically, that they market to more advanced amateurs, and then they have their, what I would consider unethical entry-level departments, which are unrecognizable. They just make them out of plastic. very cheap aluminum. They're poorly manufactured. They're clumsy and awkward to set up and use. Orion's philosophy is to build a good telescope, so with the same kind of engineering practices that you'd use to manufacture a high-end amateur telescope, but applied to the budget kind of entry-level designs. So they make smaller telescopes, but make them very well. They tend to have all metal parts. Everything is aligned really well and adjustable. They use the